Okay, so hi, I'm Moll, and I work for NEC, and we have a vector CPU architecture that I'm presenting here as a new target for LLVM, and it's a scalable vector playground, so actually hardware that's available today, and this is joint work by a lot of people at NEC. So first of all, what is this about? So this is about the NEC SX-Aurora vector computer, which is basically a vector CPU on a PCIe accelerator card. And you find that in HPC applications, so you have cluster setups, and this is basically an HPC workhorse, so yeah, usually simulation codes. It also works in memory databases running on that card. And yeah, so show some of the specs below. And we're adding this now as a new target to LLVM. And this is a vector CPU, so there's some unique challenges if you're targeting this, right? So vector CPU means it's basically like a SIMD architecture. So you have SIMD registers, but they're very wide. So you got 256 elements on one of those vector registers. That's the first point. So the second one is you have full vector predication. That means all SIMD instructions are fully predicated. And third one, and this is special about vector architectures, that's different from SIMD, you have a vector length register. Okay, so if you apply a SIMD operation, it's not only applied with a mask bit is set, but also only up to the limit of the vector length register, right? So on the slide here is shown that if the vector length register is set to 6, then you will only compute results up to the sixth lane. And this opens up some unique code generation challenges, which we do not have in other architectures right now for LLVM. This also comes up, for example, in the RISC-V extension, so there's some overlap here. And the problem basically is you have this global vector length register that affects all SIMD operations, but there's no obvious dependence between the vector length and the operation. So that's not encoded in LLVM, IR. And so the question is, how can we handle this dynamic vector length on the R level? And then another feature is if you have a vector operation and it's only applied to up to the vector length index, then you want to do partial updates. How do you do this? And so what we do is we basically add the vector length as an explicit operand to each SIMD operation. And then later on, we have a pass that translates that operand into updates to the vector length register. And this pass is designed in a way that it's only updating the register when necessary, only when you change the vector length between operations. And this is something you want to add to LLVM, contribute. And all in all, this is now available. There's a backend available in GitHub, and we're planning to upstream it. The first patch is out of Fabricator. And so we'll have, ideally, NEC SX-Aurora as a prime target for LLVM that you can use as a playground for vectorization and what have you. And we're looking for collaborators. So academic collaborators, for example, if you want to use this very interesting new architecture, if you want to solve interesting problems in vectorization, come talk to us. We also have a poster later at the poster session, so just come talk to us and we'll see what we can do. We can maybe even give you access to the architecture. Right, and so one thing I want to say is that there's this LLVM-VP proposal we've been working on. So VP is about adding vector predication support to LLVM, because LLVM doesn't support predication very well right now. And we will use that for our target once those patches are in, once this is in LLVM. All right, thank you. Come see us at the poster session.